Okay, so I'll start. The first presentation I'm giving is about MHC class 1 peptide processing and immunogenicity predictions. We know, you've heard a lot about MHC binding, and we know that there's other factors that impact if a peptide can be recognized by T cells. And the two things I'll talk about is processing, meaning which peptides actually get made by the cell and are available for MHC binding, and then immunogenicity prediction, which essentially is asking, are there certain properties of a peptide that make it more likely to be recognized by T cell receptors than others? And for some background, what you see here is that I'm not the best graphic artist. I have to label the things I draw. So this is a mouse and this is a virus. I added ears to the mouse because before that it looked like a sperm. So if you have a virus infecting a host, what happens is that it enters cells inside the host, replicates there, and spreads throughout, and that's obviously how you get an infection. So to clear an infection, antibodies stay circulating and can directly detect the free virus, but somebody needs to get at the virus inside the cell. So there's the mechanism that has evolved to do that, that actually everything inside the cell is constantly subject to degradation, and you'll have proteins that are cut to peptide pieces that can then bind, some of them, to MHC class 1 molecules, which are then targeted by T cells, right? This is essentially what we've heard the whole time. And now you're getting your T cell response, meaning you get killing of the cell, you get release of cytokines that can attract other immune cells, you get proliferation of these T cells that form a memory set that can then quickly react to other virus infections later in life. So again, when we do T cell epitope mapping, we want to know what are these peptides that can cause such a T cell response. We've talked a lot again about peptide MHC binding, but there's other factors involved, such as who is going to get made. So when we look specifically at what these mechanisms that are involved in peptide MHC ligand generation, we have this turnover of proteins that are cleaved by the proteasome into individual peptides. Most of them are destroyed and made to individual amino acids that are reused for resynthesis, but some of the peptides can bind through a transporter called TAP, get transported into the ER, where they can get cleaved again from other proteases like ERA, then can load MHC class 1 molecules if they have the proper binding motif, and can be transported to the cell surface where they get scanned by T cell receptors. And so we've done a number of studies estimating the importance of these relative steps towards what epitope actually can make it from a given protein to the surface. And roughly 15% or so of all peptides that you can think of, we have evidence for that they can be generated through this processing mechanism. Then about roughly, between 1% and 2.5% are capable of peptide MHC binding. And peptides that are bound on the cell surface that in the proper MHC context, for about half of them can be found in T cell repertoire. So this is the reason you can see here is why we focus so much on MHC binding. It is by far the most selective step in this process. But the other things play a role as well. And so we have different predictors that allow us to get at this other steps. And I'll talk first about the combined predictor that adds proteasomal cleavage and TAP transport to the binding predictions. So you find that here on the homepage for the analysis tools. If you click on that, you come to this page where you now have a very similar looking interface like you saw before for the MHC binding predictions, where you can enter your peptide here and define the MHC allele of interest, but you have these additional fields down there to classify proteasomal cleavage and TAP transport predictions. Proteasomal cleavage, as you saw in this previous slide, it generates the C-terminal end of the peptides. And there's two different versions of the immunoproteasome and the constitutive proteasome. And these were characterized based on in vitro digest, where essentially you take a protein, you throw it together with a bunch of proteasomes, and you detected the fragments that were made by mass spec, and based on that try to identify what are the cleavage motifs that are actually enabling the proteasome to separate out the break amino acid bond. So these, the default here, the immunoproteasome is made in cells that are under some kind of inflammatory conditions, so that's presumably the most relevant one, which is the default. Then the next thing here is the TAP transport, which has two other parameters, which are essentially estimating what is the spectrum of extensions that you have in your of the peptides that are being made. So these two parameters, and you can read them up in the original prediction method paper that described this at first, are kind of like a statistical distribution, estimate of the statistical distribution of the different extensions that you have of peptides before they get trimmed in the ER. And as we would normally recommend to not changing these at all, because this was the one that worked optimal. And when you do this now, you're getting a similar kind of feedback back as before, where you have the individual peptide sequences. And now you have, in addition, the proteasomal TAP score. This MHC score is minus log IC50 of the nanomolar, just to make positive scores better. So that overall, we then have a total score where essentially you just add up these three, and that's then what you can use instead of your just binding score in order to identify epitopes. So you see here that there's a vastly different range of variants. So the proteasome has a range of 1.7 versus TAP of 2.8 versus MHC of 6.7. This again reflects that, so essentially the range of values you're getting from like very good binder to very bad binder differs a lot for MHC versus TAP and proteasome matter a lot less. So ultimately, when we run these and evaluate how well they work, what we can see is that they are much better, they are significantly better than just binding predictions to predict eluded peptides, so peptides that are naturally found on the cell surface. So clearly it seems that these predictions work. However, when we try to see, do we improve our ability to predict T-cell epitopes, we don't see convincing evidence that we really get better. So some of the issues are potentially that all this was done on human proteasome data, and there's somewhat limited data available. The TAP has different specificities for human and mice, and most of our well-defined epitope data at least used to be in mice. And also, actually, what I think is more important is that when we look at eluded ligands, we often have kind of the best case scenarios. You get the tip of the iceberg of the very best peptides from cell peptide elution experiments, and they might just have the best proteasomal cleavage, the best TAP transport, etc., which gives them a large amount of peptides on the cell surface, which might not be necessary for T-cell epitopes. There's reports that down to 2 or 3 peptides on the cell surface are sufficient to initiate T-cell responses that you could never detect by mass spec. Yes, please.
Well, I'm curious. So, if you look at the sort of the inverse problem, one of the things that's very important in HIV is both escape from T-cell receptors and escape from processing. So the typical pattern you'll see is immune system comes on, you get mutations at the epitope, then you get mutations outside the epitope, after which CTL drops away. So have you looked, and would it be useful to look at empirical studies where we suspect there might be a processing mutation?
Yeah. So the other thing is, I don't even know where I have it on the slide, but very often it is hard to tell what is, if you have a mutation outside of the epitope itself, it's pretty clear, right? So that if you have a residue that's not part of the epitope, but it's inhibiting proteasomal cleavage, that's really clear. But most of the time, the mutations we're seeing, actually the most important residue for proteasomal cleavage is the C-terminus of the peptide itself, where then actually when we look at the sequence preference for humans, there's a high degree of overlap of what the immunoproteasome likes to cleave and what MHC molecules like to bind. So it ends up being that the same mutation typically escapes both. And so that's actually also one of the reasons why we don't add so much. There's actually most of the good MHC peptide binders also have the motif for good proteasomal cleavage and TAP transport. So you're kind of not changing the order too much. Yes. But HIV is great for these studies where you really look at escape. Obviously, that's not the kind of data we typically have available for most other pathogens.
And this is all focused on epitope length peptides, right? You're focused actually on the within the epitope rather than looking at
epitope regions. Yes.
Outside.
Yeah. But obviously, when we do the predictions, you're running the whole protein sequence, and then we do have that effect. So.
TAP is also polymorphic. Is there any evidence that polymorphism in TAP affects the overall efficiency of the molecule?
So we don't have data for that. So I mean, we were working with Robert Tempeh and Peter Van Emert, who were pretty much the two only people who were doing quantitative binding assays for TAB, and they have not done the different isotopes. I thought it wouldn't affect. I think they look differently. I mean, the crystal structure is out. I don't think the polymorphisms are in the region of the, but it could still be affecting things like length preferences or other things that are not immediately apparent from the binding side. So yeah, good question. Okay, so these are the and if you want here, this is the attempt of trying to separately model the proteasome and TAB and MHC binding is also an attempt of a biological understanding of the steps towards epitope recognition. There's another approach which is saying, okay, why don't we just look at the outcome? Why don't we? Yeah, actually, let's just jump to that. No, I should be going to this. Sorry. So that there's a separate attempt which essentially uses MHC ligand elution data rather than in vitro digest of proteasome to model the cleavage process by just saying like which ligands do you find on the surface and saying that the C-terminus must have been made by the proteasome, so thus you can learn the cleavage mode from it. And that's the approach in the NetShop algorithm where you have the C-term version, the C-term 3.0, that's the C-terminus is trained on MHC ligands. And so essentially if you're a purist, you can say, well, you don't really know for sure that this is the proteasome. And there are other proteases that are potentially involved in generation of MHC ligands. But at the same time, you can also be not a purist and say, I don't care. Ultimately, this is the motif that you have on ligands on the surface, so that's what you learn, so that's good. So essentially, this is the same kind of interface and approach. They work with this NetShop algorithm, and you have the combination of them with the NetMHC, which then makes it a NetCTL pan predictor. And they also use actually the same TAB predictions that I showed you before. So, and the same caveats that I mentioned before about the other methods apply here. So in practice, we have our recommendation would normally be that these methods are, if you really want to cut down on the set of peptides that you can test, I would use them. If you have enough throughput to just do MHC binding only, and you might test a few that have processing problems, that ends up being much less of a hassle, and the chance of throwing the baby out with the bathwater by eliminating too many peptides that are actually processed just fine is more of an issue. So, I mean, specifically as in just these predictions aren't as selective, they don't work so well. MHC binding is just easier to do, so that's why we focus on them. So, and then we have a completely different approach, which at this point we have only the NetMHC and the MHC-NP implemented here, which is directly learning from eluded ligands, essentially in combination MHC binding and processing. And this was an approach developed by a Canadian group, and they have generously agreed that we host that tool. It has actually performed very well in a prediction contest, and so there's a limited set of alleles available, and again, like this is now predicting directly naturally processed ligands. So one of the reasons why we don't use it so much is the limited set of peptides available, and also in our own subsequent evaluations, the tool didn't really perform as well as we had seen in the past. But yeah, so and unfortunately they haven't been developing new versions of this. So the one that's come out at the end of last year, and we really need to get it on the website, is an approach developed by Morton's group, again using the pan predictions approach of training a neural network to simultaneously learn from different MHC sequences and peptide sequences how to predict peptide binding across different MHC alleles. But here now training together with binding data and eluded ligand data, and essentially having a shared set of hidden layers in your neural network that essentially learn the peptide MHC interaction patterns, which are where essentially then you're training essentially through these two different nodes with your different combined data sets, and we could show then that this works better than training with either one alone. So, and at the same time, we still have the same caveats as before. So we actually think that this is the best way to predict potential T-cell epitopes at this point, but the difference between the binding and the eluded ligands predictions is still relatively small. And that's why Berkeley is working on this. It's going to make everything much better with the way to, I don't know, he said in March it's going to come.
No pressure.
Okay. So then, so actually one of the important things here is ultimately, if you really care about MHC binding predictions only, predictions that are trained on MHC binding affinities work the best. If you really care about eluded ligands only, predictions trained only on eluded ligands work the best. Normally, we actually care about neither. Normally, we care ultimately about T-cell recognition. And there, the differences aren't as great as when comparing these two. So you find a lot of claims currently by people who are doing a lot of mass spec data that they are so much better than everything else in their predictions, and the only thing that they test this on is their own mass spec data. So that's been the problem. This is the cancer field. Okay, sorry, small rant. So let me move on here to the next set of tools, namely the immunogenicity predictions. And Sandeep is going to talk later about class 2. This is just for class 1. This was our first attempt where we just looked for, okay, if you have a set of peptides that binds perfectly well to MHC but is not recognized by T cells, that's in white, or you have a set of peptides that is binding at a similar level to MHC and is recognized by T cells, that's what we have in black. And then we look at the distribution of amino acid in these peptides. The frequencies compared to red is what you would have in the same set of source proteins. You will find that some residues, say the charged one like E and R here, tend to be low in general because they tend to be bad for MHC binding. But then and losing here is good, versus like the tryptophan is specifically enriched in immunogenic peptides, which there's actually past experimental studies that also back this kind of up. So you have tryptophan, lysine, and methionine, where this kind of makes sense, which are kind of, how do you say, like non-bland residues. They might be better for TCR interactions, as in they might be more noticeable. The thing that totally surprised us was the serines also, where you wouldn't think of that happens. They're also quite enriched here. Yeah, well, no, oh, this is the just fine, sorry. They are enriched in non-immunogenic. So ultimately here you see these preferences, and then we can use them to make a score. So you enter your peptide sequences, and this evaluates only the residues that are not anchor residues, or not typically anchor residues for class 1 binding. And then we're calculating essentially a sum of these propensity scores, which gives you an overall score, which is saying does the residue composition of this peptide, is that associated with immunogenicity? And when we evaluated that on the set of left out epitopes, this is the kind of data we're seeing. You see epitopes tend to have higher scores, versus non-epitopes are like half-half. So if you're saying, okay, I'm only going to take, and this would be our recommendation, things that have a score greater than 0 in this immunogenicity, you're retaining 85% or so of your epitopes, and you're throwing out half of your non-epitopes. So again, you're enriching your set of data, but then it comes back to the same kind of thing. What do you want to do that? You are missing. You are going to throw out some perfectly fine epitopes that don't fall in this region. So if you want to save a lot of money, it's useful to do it. If you have enough money to just screen everything, again, you would stick to MHC binding, which is where this would be looking much more skewed towards binding being a predictive factor. Okay. So that was my first part of the, any questions on this? Yes?
So there is a histogram in the previous slides. There is a red color dash, like those slides.
The red one is the frequency of this residue in the source proteins from which the peptides were from. So this is like the overall amino acid frequency independent of binding or immunogenicity. Okay, so now let's go to the next one, which is much longer, so I'm probably a little behind. Okay, so so far everything was prediction tools. now I'm going to talk about analysis tools. And I made these arrows, and I don't know what I was thinking. So I'm going to cover not just these three, but also cluster analysis and the rate tool. And yeah. Okay. So I guess I should say, if you go to the Analysis Resource website, there's this tab with analysis tools. That's where the starting point for every single one of the tools that I'll talk about is. So population coverage. The idea of this tool is to calculate if you have a set of peptides where you know the MHC restriction of them, in which context they are recognized, and you're asking, is this, if a combination of these peptides, is that a good pool that would be recognized specifically if you map them in one population and you now go into another, where the MHC frequencies of different HLA alleles might be very different. So this is essentially, it is looking at HLA frequencies that we're taking from allelefrequencies.net and using them as follows. So this is the home page, and as a query, we have, and we can get to that actually using the example data set. There's a set of 11 MHC class 2 restricted epitopes that were defined as being promiscuous HLA binders. And the question is, if you were using them, these are actually HIV epitopes. Ha, you're stealing your guys' stories. If you use them in North African settings, would they be having appropriate population coverage? These were mapped actually in the US population. So these would be the different epitopes from HIV, and these were the restrictions that were defined from them experimentally. So that's the kind of thing that you would know based on your data. You select the populations that you're interested in, and the availability of these populations is directly driven by where can we get HLA allele frequencies from allelefrequencies.net. If you then hit compute, you're getting this kind of overview table where for each of the populations you have your projected coverage, meaning how many people in the population are expected to react to at least one of these epitopes. And this is kind of the detailed graph showing you just for one of the countries, where you now see for, like in this example, you have 22% of all people, this is the X on the left side, would have no responses to any of the epitopes. And then you have here about 20% recognize 2, then you have just very few here that recognize 4, etc. And then you have the cumulative graph, and one of the numbers that you can use to evaluate is the PC90, like at 90% of your population, how many epitopes would they recognize? That would be 0.88, so this would be not a really great set of epitopes to use. So again, projecting out population coverage based on HLA frequencies. The next tool I'll talk about is epitope conservancy analysis. Here's the idea: you have a set of epitopes of interest, and you have a set of protein sequences, and ask, how conserved are the epitopes that you have in the set of proteins? And the defining degree of conservation based on the percent of sequence identity. Somebody you mentioned Hamming distance recently, is just aligning your epitope to your source protein, look for whether you have the best match in terms of highest number of residues conserved between the epitope and the protein. And we use this here as an example, and that's actually one of the reasons why we developed this, reason to put it on the website, is when the swine flu pandemic came out in 2009, one of the questions that came up is, are the Tcell epitopes that had been previously defined before 2009 going to be recognized again in this new swine flu sequences? So this is just the tool, and we put in here known epitopes that were mapped prior to the 2009 pandemic, then added here. At that point, there were 55 different pandemic flu strains available, and the question was essentially, can we find with these epitopes in these different flu sequences? Here you just see, I mean, there's a lot of more data here. You just see one of the hemagglutinin sequences where there's 55 strains that had up to 10 proteins each sequenced. And when you hit submit, this is the kind of data you're getting, where for each of the epitopes, you're getting your percent of proteins sequences that were inputted that were matched at 100% identity, and that's something you can vary as a parameter setting. But in this case, you have, for example, that this sequence here is found in 55, so actually one sequence of all the 55 strains had this peptide conserved in it, and you can look at that in detail, and you see here that all these different swine flu strains here contain these epitopes. And we actually did synthesize these and test them in people, and actually could show that there was a perfectly reasonable T-cell response to swine flu strains that were kind of ignored at the time, or people didn't appreciate it fully because everybody was focused on the lack of antibody responses to them. So that was what we used the Conservancy Analysis for. Next example is the epitope cluster analysis. When you, very often if you have data from the IEDB, or even if you generate yourself, what happens is that you end up with peptides that are very, very similar to each other, and you might actually have essentially multiple copies of really the same epitope in there. We've been using this clustering tool for quite a bit, and then Sandeep actually made a new version of this tool, which is I'm going to show you, and we should actually remove the old version from the website, which really is inferior in every aspect. So this is just a very, very simple example just to show how this works. When you go to the cluster analysis, you have like 5 sequences here. You can obviously already see that they are quite related. When you click on, obviously this is where you enter this, or you enter a file, you click on go step 2, then you're here and get the choice of selecting a sequence similarity threshold that you consider relevant. So if you choose 80% here, and then go to the last step, there's 3 different clustering methods. One looking for actually clusters, the other one for clicks, and the second one that is custom, that kind of combines properties of the 2 of them, which is the default setting and we would normally recommend. How this works is as follows. You first start off, essentially this is done internally. The program compares every pair of epitopes and asks what is the sequence identity. And so in this case you have 4 out of 5 matches, that is 80%, that was the threshold we consider relevant. So all of these are related at an 80% threshold, versus these guys only have 60% similarity. Yes. So you can represent that data in a graph-based form, where you're essentially saying every 2 peptides that are similar at the threshold level that you care about get connected, and you get this kind of graphs where the nodes are your different peptides and the edges are connecting things that are similar. Yes?
Does the software draw the graph?
Yes.
Okay, nice.
And so then when you look at this, actually in graph theory, there's 2 ways to look at this. A cluster is a set of peptides that is somehow connected, and you can imagine there might be another connection out here to another one out here. Then you might end up with a cluster of peptides where any 2 are actually not necessarily that similar. There's just a path in there somewhere. Versus then there's a click that's like these 3 and these 3 form a click, where there's a complete connection between each of them. So all of these are similar to everything else. And depending on what you want to do, say if you want to just have 1 representative peptide per click, you would do that algorithm. If you just want to know which ones of your peptides are somehow related, you use the cluster algorithm. So as an example here, here you have it. This is the graphical visualization you can pick. And so this is actually putting this side in and then running it, and you get actually to view the cluster. That was the question. So as an example of where we're using this is a real-life example where we had done studies for Tcell epitopes in mouse proteins. So we synthesized peptides overlapping these mouse proteins and tested them for Tcell recognition in people who are mouse allergic, and identified 23 peptides. And these mouse allergens are highly homologous to rat proteins. And we essentially asked, is there an overlap between the T cells identified, the epitopes we identified in the mice versus the ones that have been previously defined in the rat, which we just queried from the IEDB. So then you have your named peptides, and you see here, then you run your cluster tool, that in this case here, the first cluster contains 2 rat and 2 mouse peptides. The next one also 2 rat, 2 mouse. Here you have 1 rat, 1 mouse. So you have a number of overlapping ones. Down here is the singleton sets out, all the peptides that are just one after each other. And when we looked at this, so we had a total of 30 clusters, 22 of them were singletons, the other ones, there were 8, and there was on the last slide that had more than 2 peptides. It was actually quite nice and striking. And when we looked at the reactivity, that the ones that were overlapping between rat and mouse were the ones that were recognized the highest, where you can then actually argue, and this is something that comes up repeatedly in our studies, where you don't actually, it might very well be that they are more immunogenic because they're conserved. And people who are allergic to rat, they're also going to be exposed to mouse and other things. And you essentially have the same set of epitopes stimulating and driving your T-cell immune response. In allergens, there's definitely one of the potential mechanisms how you get one allergy first, and then you tend to get more and more as you go through life. So the next tool is the rate restrictor. How much time do you have there?
15.
Okay, so I'm in perfect time. Good. I can slow down.
Plenty of time.
Yeah.
25.
Oh, you better. What happened?
I don't know.
Okay, so the rate tool. So inferring HLA restriction specifically for MHC class 2 molecules is absolutely non-trivial. For MHC class 1 it works quite well because the different MHC molecules have quite different specificities. And if you very often you take the MHC molecules from a given person, you predict the binding affinity for your peptide, you already know quite well. And there's also reagents available that very well allow you to distinguish which allele restricts it. For MHC class 2 molecules, because there's such an, you saw from the promiscuous prediction approaches, there's quite a lot of overlap between different alleles, and it can be much harder to define what is the specific MHC restricting class 2 epitope. So what this tool does is have it to take a completely different approach and ask, can we infer the restriction based on the HLA typing information for the donors that we have, and just see like which donors react to a given peptide, and ask them, is there an enrichment of certain alleles that are in those donors rather than others. So this is the kind of this is the homepage of this tool, and it requests that you enter allele data for the donors, essentially what is actually typing data, then response data, like what peptides responds to what, and I'll show those in a second. And these are just tab separated files in plain text format. And I mean, you can save an Excel file into that format, say, which normally is what people start off with. So this is the input data in terms of MHC alleles. So for each donor here, the loci should always be aligned. You have your DIB1, 3, 4, DQA1, DQB1, DPA, DPB, typing information for each of the donors. And then you have the response data, where for each of the donors, you have, in this case, spot forming cells per million. That's a readout from an ELISpot assay, which essentially says how many of the T cells can respond to this peptide. And there's a threshold, I think that was back here, yeah. So you can say, like, say, we typically use a threshold of 20 or higher is what we consider a positive response. So that is then used to define, like, say, these we will be responding donor to this peptide, but not this peptide. So then, based on these data, we can calculate an odds ratio, which is simply if you're taking the frequency of donors that have the allele and respond, and the donors that don't have the allele and don't respond. If that is much higher than the cases where you have mixtures, so they don't have the allele but they respond, or they have the allele and they don't respond. So if this is high, then your odds ratio is high, which is just the standard odds ratio you would have in clinical settings or so, meaning that there seems to be an association of the allele and of the donors expressing the allele and responding to the peptides. Actually, quite related term is the relative frequency, which does a similar calculation, but has the advantage that if you have zeros down here, this is going to be infinity, and this is always calculatable. So this is the kind of output we are getting. We have the this is actually running the sample data, and when you then, this is the output we get. Sorry. So these are now sorted, looking at, you have your individual peptides, you have the alleles, and then you have essentially the summary of these counts, in this case, there were 6 donors that have the allele and responded, no donor that had the allele, no donor that responded that didn't have the allele, and they were, and there were 18 donors that had the allele but didn't respond, and 26 donors that didn't have the allele and didn't respond. And based on that, you can then calculate your odds ratio and your p-value, if that is significant or not. And what's shown here is the ones that were considered significant. Then you have obviously much more. You have a complete report where all of the data is listed, including all the ones that are non-significant. If you just to sanity check, say if a specific restriction you're interested in, why didn't get picked. Yeah, that's the rate tool. And that was, I mean, the two applications I showed you before, there was quite a lot of work going into the validation of this tool where we could then experimentally check how well did this predict, and it worked quite well. Then the final one tool I'll talk about briefly here is the EPI Filter tool, which is essentially an extension of the IEDB query mechanism. So when you look at the IEDB search results for something like, say, hepatitis C virus or so, you'll have 10,000 entries easily in there. And one of the common things that we do in the lab, and other people use the IEDB for, is to identify a set of epitopes that you use as a cocktail to get at T-cell responses that are reactive to that epitope pool. So this is essentially a post-filter of IEDB query search results, where we've taken essentially a heuristic approach of defining, counting like how valuable are the different assays we have, and really defining epitopes, and then ranking them based on that. So I'll walk through this. So this is actually, I just realized too late, is out of date. You need to click on the export epitope results, and then there you'll have EPI Filter as one of the options. So you can run any query you have, and then start this EPI Filter program. The next pages are just exactly the same. Then you're getting here, and get the choice between what type of epitopes this should be further filtered by. You have these advanced options here, and this is really where the interesting thing is. So here you have, I would say, pretty much exactly Alessandro said in the box, what assays he thinks are the most relevant ones. So say if you have an epitope that is positive in an MHC tetramer staining assay, you'd give that more value than if you have, say, a proliferation assay. Or if you have a crystal 3D structure, you give that more value. So essentially it is completely heuristic, and you can completely disagree and change these values to anything you think is important for your application. But that's the idea. It's essentially assigning these scores, and then you get these kinds of outcomes where you have now your for each of the peptides an overall response score based on the assays and that are used to define it, and the different studies in which it was defined, different studies in which this essentially the response frequency, how many people were tested and how many responded to them. So, and when you can export these results, and then you have them in the spreadsheet. And with that, I'm done. Yes, please.
So for the rate tool,
Yes.
can you just, I'm unclear on if that is, if you can actually incorporate actual HLA binding data into that you have, or if it's just based on your predictions.
So that is just based on the frequency of the given alleles in responders and non-responders.
Okay.
So what we usually do, we do combine it with predictions, because you're probably aware of the fact that HLA molecules are in tight linkage disequilibrium, so that if you have a peptide that is restricted, say, by the R beta 1 or 301, that gene is also in very tight linkage disequilibrium with HLA DR beta 3 or 101. They're right next to each other in the clones. So people that respond to that peptide will be enriched for both. What you can do is, okay, you take the list of what shows up as significant, enriched, and then say, oh, okay, let's see what this peptide is predicted now to bind to that gene, that HLA, but not the other one. So my bias is that probably that's the right one. So the rate is really giving an inference. The way I look at it is that it narrows the universe of choices, in the sense that the common sense is if a peptide is restricted by that HLA, you should find that HLA in people that respond to that peptide. right? So basically you start, your patient population might express 300 different HLA molecules, but you can quickly narrow it down to very few choices of.
So, but it's something we had thought about adding it. That's why I wanted to test you to make sure
Yeah,
that
we
it wasn't added. And
we
it's-
did, but it was.
It was hard to automate it, so we just wanted to kind of give the whole data, and then people can look at it and send it. There's other things like also this has separate associations for the alpha and the beta chain. So that's one of the other things. So in the case of DP and DQ, you'll have to do some manual post hoc analysis. What's the likely coupling, and then go through the binding prediction. So, yeah. Any other questions? We can easily do lunch. Oh.
Oh, sorry, can you go back to the clustering graphic?
Uh-huh.
So the ages you mean is the that one. So the ages you mean is the percentage of similarity?
It's like everything is connected that has at least 80% similarity.
What about the size of the nodes represent? Because the next
The next one is bigger, right?
Because it was mouse over, it was zoomed in to show the peptide sequence.
this
okay,
one,
okay.
the size of the nodes represent.
Yeah, so this is just because, so okay, we should look at the tool. Let's try it.
Yeah.
Thought I had the. No.
Go down, go down.
So it's the cluster 2.0 tool. So this is a much larger example. So it might take a bit of
Could have
time.
picked the same example that I did mouse one.
Sorry?
Could have picked the same example that I did mouse one.
I
It
like
was
this.
bigger.
I want it to be bigger. Do you think it's going to take too long?
Probably.
1 minute? Okay.
Yeah.
Okay. So here you have the this data. This is actually from ligand dilution data. That's a good example where you get a lot of overlapping hits because you get different extensions of the same one. And here you have the clusters that come out of it. And when you mouse over it, it gets bigger and it shows the sequence. And because the screenshot was taken with a mouse over, that's why it's bigger. But otherwise, they are all the same. And you can do fun things like pull them around and stuff and play. I do that.
So is it every time show the same percentage, the similarity?
Well, you can change these things here. So if you're start over, let's do another example. So this is the algae example that I had in there. So here you can change what percentage you
Can
want.
you show all at once? Like the length of the edges, show like long
Difference,
meaning 100% and then short.
That's so that would be possible, but we didn't do it. So.
Because this every time will show the same length, right? For
Yeah.
this- I just like get.
So it's more like, I mean, this is like using, what is it called? Is it Cytoscape still?
No, it is D3 library.
What is it?
D3 library JavaScript.
So yeah, so we're using essentially an existing peptide library and then, yeah, doing things like changing this. I don't know if that would be possible. I'm not sure. I don't know. I like this. Okay. Yes.
In one of the slides you mentioned when we talk about the MSC1 prediction.
Yes.
So the binding affinity, if taken alone, predicts better, performs better, and the neutral ligands perform better separately. So when you combine both, they are not performing as expected.
Well, they're not performing clearly better. And okay, what's the question?
So the question is, so the data for the two aspects for the same subject, do we have the data for the both of the like the binding affinity as well as the elutive ligand?
Okay. So in some cases we have binding and eluted ligand, and the overall is a good correlation. But there are some ligands that get eluted that are borderline affinities, and there's very often there's many more peptides that are capable of binding that we don't find in the eluted data. Generally, the eluted data tends to be a small subset of the peptides that are there, and that's typically just because the resolution of the data doesn't go down far enough. Does that answer the question?
So yeah, we can talk offline more about that. I mean,
I'm not much. You have to run to an airport pretty soon.
it's okay. We can follow with the email. Thanks.
But also, there's lots of people here.
Sure. Fine.
Okay. Yes.
Okay, so really quickly, before we break for lunch, I want to point out Jason in the back, Jason Greenbaum. You can bother him about licensing, or Hayuk, who's sitting right next to him. So if you're interested in licensing or have questions, you can bother them. There's also, if you're just curious, there's the FAQ, frequently asked questions sheet up here, and you're more than welcome to grab one. And it's also saved on the Google Drive that you were shared if you just want an electronic copy for reference later. In terms of lunch, same exact place as before. We have an hour, and so we'll just give it exactly an hour. That way, if we can have more time in the afternoon, that would be great. So why don't we just reconvene back in this room at 1:05? Otherwise, lunch is the same.